Maybe the audio, yeah. Oh, now we have the echo again. Good. Well, how many minutes does it now need? 4. Okay, I'm quite impressed with myself. Right? You should not be impressed with yourself too often, but voicing this now and then is, I think, fair. Good. Let me turn off any notifications. They're distracting. Good. So, yeah. Welcome, everyone. I hope everybody is doing well. I hope you're enjoying the semester so far. Yeah? Is anybody saying, okay, please let it be over? No? Okay. Or you don't dare say, because then I maybe ask why, and is it me? And maybe the answer is yes. Who knows? Who knows? Good. Yeah, today is a bit of an exciting day for me. Not so much because this is lecture number 6, but today is the day where we're going to be hearing whether the proposal that we handed in, well, we started it 3 years ago, the whole process, for a so-called cluster of excellence. An excellence cluster, this is the largest funding instrument of the German Science Foundation, the Deutsche Forschungsgemeinschaft, DFG. And if we get the money, and we is a large consortium of 24 PIs, principal investigators, and at least as many principal researchers, PRs, so it's a large consortium. And if we get the money, it means that we get 70 million over the next 7 years. That's sizable, right? So it's on the topic of AI-driven drug discovery and development. I would say societally quite important, right? Together with our friends from across the road, from HIPS, people at the University Hospital in Hamburg, and a number of the computer science, AI people, and the bioinformaticians here. So, and we defended this proposal in November for a live audience. And until now, it was just waiting. And I have to say that for the last few months, it was very far in a dusty corner in my brain. I knew it was there, but today I'm excited. Well, let's see what happens. I really hope we get it. I really hope we get it. It's a very cool topic. It's cool people. Let's see. Has nothing to do with you, at least not at this moment. But although if you do very well in TADA and one was like, hey, I want to do a PhD, maybe this 70 million, a small part of you could be for you. Who knows, right? But otherwise, good. Okay, lecture 6, causal discovery. We're picking up where we left off last week, which, well, quite literally was in this lecture, right? I mean, as you see, I did update the date, right? So now we're not in 2024 anymore, but the first few slides are exactly the same. And I'm just going to skim through them, given that we already went through it last week, and it's already part of the recording, so we should not waste too much time there. The general idea of these weeks is, what is causation? How can we measure it? How can we discover it? And the discovering causality from data is the theme of today and also a little bit next week. So overall, we have some data. I mean, I don't draw it as a table, but these are just variables, and we would like to figure out which one causes what. And ideally, not the goal of today, but of course, ideally, we don't just want to know, is there an edge and what is its direction, but also, well, what is the shape of the edge? What is the function behind it? For example, is this caused by one function that takes in y and q and does something messy to it? Or is it just that y causes t and q causes t? Traditional example is that if y would be rain and q would be a sprinkler, then t could be, well, the grass is wet, right? Or you are wet if you're standing wherever it's. So, of course, these are two, well, separate mechanisms. Sometimes you also have necessary mechanisms, right? I mean, if it's, let's say, fire, you actually need multiple things, but let's say oxygen is plentiful, then we definitely need some fuel, right? And we need a spark. Otherwise, it's not going to happen, right? So that's a very different type of function. This is not really what we're going to be looking in today, but over the course of next week and a little bit after, we will be looking into finding these structural causal mechanisms in their fullest. What you hopefully remember from last week is that getting causality from data and data alone is a pipe dream. It's not going to happen, right? We're stuck on rung 1. From data, we can only get associations. What we saw then last week is that if you somehow have knowledge or a belief about how the variables are causally related, then using do calculus, you can sometimes figure out that, hey, wait a second, we don't have to run a randomized controlled trial. We can actually, given the observational data we have, we can estimate causal effects. But, well, this is one of those shit in, shit out type of situations, because if we have the true causal network, all is fine, right? And our analysis will be correct. But if our input, the causal network, is not fine, if we made a boo-boo, then yeah, the analysis will be correct with respect to the graph, but not in general, right? That depends on how bad the errors are. Just as an example here, suppose that we missed a number of the edges. Suppose that I missed the edge from x to y. How bad is this? We can argue about this at length. Suppose that I would have reversed the arrow from y to x. How bad is that? And how does this compare to missing the edge altogether? Well, that fully depends on the type of analysis that you want to do, right? But if you want to change the value of x right now, you would know, okay, well, you need to basically pray to the gods of x, right? Otherwise, there's nothing going to happen, or basically the exogenous input to x you would need to tinker with. If we would have flipped the arrow the wrong way around from y to x, you might be tempted of starting to poke at y, which corresponds a little bit to, well, moving the needle on the gauge rather than, well, putting additional pressure into the tank, right? So suppose that we would have missed this edge, well, we would not have played with the needle. We would have, well, basically said, okay, well, in order to change x, we need to affect x directly. So in a way, not having the edge might have been better than having the wrong direction. Just to illustrate a little bit that these beliefs are very important. And yeah, how to now even measure how good a graph is compared to a ground truth graph is already problematic by itself. Okay, so last week we were given a graph. We assumed it, we believed it. Right now we would like to discover this graph from data, which is impossible, so we need other ways to climb up the ladder. We need assumptions about how we think the world works. How can we climb the ladder? I mean, well, we need assumptions. I mean, I'm going to skip through this because we discussed this last week in quite some detail, so I want to have this slide. We need to have assumptions that the data we have is generated by something that we can actually extract from the data. And that means that the edge from data to graph in this particular case is obvious. How could you otherwise go back? But we also need to, very importantly, have the edge from the graph to the data. And that is perhaps the most sneaky one, because it's the easiest to forget, right? It feels natural to, okay, if we want to get something from data, we need to be able to get back to the model, but what models generate data that allow this? It needs to be a loop in that sense. And of course, everything is IID because, well, otherwise it would become too realistic. Under these assumptions of the causal Markov condition, basically we can factorize the joint distribution. We live in a DAG. Causal sufficiency, we have measured everything that is relevant. And causal faithfulness, the idea that if we see a dependency in the data, well, that means there is a true cause of this. This is not just happenstance. Either it does mean that X causes Y, it means that Y causes X, or, as Hans Reichenbach postulated, or philosophized about, there is actually a third variable Z that causes both X and Y. X and Y themselves may not have necessarily anything to do with each other. This is how we can then start to reason under these three assumptions of what is going on. And that gives us a way to start a process which, given data, we find dependencies and we start to reason about them all the way until we reach a causal network. And what we're now doing might still feel like we're just looking at the data, but we really need these assumptions. Without these assumptions, we can't say anything whether a dependency we found is good, is bad, whatever it means, right? So, good. This I'm going to skip. Yeah. So because we need this in a few minutes again. Suppose that we just measure that X and Y are dependent, and we do not have a third variable Z, right? X and Y are not connected to a third variable Z. Right? So there might be a Z, but it's just not connected. It's just like this. Based on independence tests, there's nothing that we can do. right? Because X and Y are dependent or X and Y are dependent, no matter what the ground truth generating mechanism is. So what can we do? Too bad, right? I mean, this edge, so if there's a true dependency between X and Y, we have to leave it undirected. This is not fulfilling and something that we will address in the following, but for now, alas. The moment that we do have three variables that are related without the shortcut, right, then there are four different ways on how this can come to be. Either we have a chain, X causing Z, Z causing Y. X and Y are independent, right? But, well, they're dependent, but they're not directly dependent. The information flows through Z, flows through Z. Same thing here, right? So Z is the origin of the information. So if any of these three is the true generating mechanism, we get the same dependencies and we can't uniquely tell it apart. So again, if one of those three holds, the best we can hope for is finding that there is an edge between X and Z and an edge between Z and Y, but we can't direct it. Not just like that, right? Too bad, sucks to be us. This case is then the odd one out, because here X and Y don't know anything about each other. They are truly independent, right? It's not that we killed the dependency by conditioning on Z. It's actually the opposite. The moment we condition on Z, we know something about both X and Y, so X and Y become dependent given Z. Unique situation, and because there's only one way to do this direction is identifiable, right? There's no other way to explain that the data we've seen, right, these types of dependencies, that those hold within the universe we constructed for ourselves. So within a universe where there's a causal Markov condition, causal faithfulness, and causal sufficiency, there is no other way than this, right? This has to be the ground truth. Just to immediately put you into the critical foot again, if the data, for example, is not IID, could be, right? I mean, that's suppose that we live in a universe where actually nature is against us, and she gave us or he gave us data that is not IID. That means that if we use a test that assumes IID-ness, we might find dependencies that look like this, even though that is not really true. That would be a bit of a pity, of course, right? With these ideas in the back of our heads, so the whole point of that, if we find a dependency, we can either explain it directly or indirectly, and this orientation that can we do? There are, I would normally say two, but it's sort of like 2.5 different ways on to do causal discovery. I'm going to discuss the two main ones in detail and the half one in quick passing. Because it's not that I don't have so much to say about it, but I just don't like it so much, and it's still a bit in development. And this one is classic, very classic even. The PC algorithm. The PC algorithm is the prototypical example of constraint-based causal discovery. And this is not constraint-based causal discovery in the sense of constraint programming of something like that, right? I mean, not really pure formal methods. No, what we do is we take an independence test or a conditional independence test. That is going to be our hammer. And we slam this hammer onto every variable that we can find in every combination. And effectively what we just did in the previous slides, whenever we don't see a dependency, there's not a dependency. If there is a dependency, can we explain it away? And then we try to do this as much as possible. There we are. We just look at conditional independences. That's what we hunt for. PC algorithm, cutely named after its two authors, Peter Spertus and Clark Glimmer. I find it interesting that they took their first names. I mean, that's, PC also sounds a bit better than the SG or the GS. I don't know, but good. It is a really classic algorithm in the sense that it's not even that mega old. It's from, I think, 99 at the top of my head, but late 90s, which of course is quite a while ago, but come on, right? I mean, let's say the A-star algorithm, search algorithm, is a bit older. Huh? What do we do? Well, first we need to make assumptions. What do we assume, right? And really, in causality, assumptions are a king, and you need to spell them out. If you don't spell them out, I do not know if you've actually climbed one rung onto the ladder, and for all I know, you have an associational method that in practice just strongly correlates with causal ground truth, but I can't say that you actually are finding causality. Data generating distribution has the causal Markov property on graph G. Okay, the world is a DAG, right? It is faithful to G. I copied this straight from their paper, these statements, right? This is how you would read them, right? Okay, causal faithfulness, right? If there is a dependency in the data, well, it has a reason. If there's an independency, it means that there is no edge in the actual graph. There's only one graph G to which the distribution is faithful. Okay, this goes towards IIDness, right? So they do spell it out, but in a slightly weird way, or weird, not that every machine learner would immediately understand it. All relevant variables are in G, okay, this is causal sufficiency, right? Otherwise we can't explain things. And no, every member of the population has the same distribution. So this goes basically the other angle of IIDness. There's not multiple distributions that everything is independently sampled from. Good. Then what are the two main steps? Because it's a relatively simple algorithm, and I'm going to illustrate it with an example. First, what we're going to do is we're going to start with a fully connected graph over the variables that we have. And what we're going to do next, we're going to use independence tests and then conditional independence tests to basically prune out edges until we can't prune anything out anymore. That leaves us with the skeleton, the causal skeleton, undirected DAG. So it's more like, it's a graph. And what we're then going to do, apply again constraint-based rules, like we've already seen previously, finding these colliders, right? But there's a few additional ones, and that allows us to orient some of the edges. And then we arrive at, well, if we are very lucky with a DAG, more often we get a partially oriented DAG or a PDAG, and yeah, sometimes we can't orient anything, well, then we're just out of luck. So this is the starting point. This is what we want to find. How do we do this? We draw all possible edges. So I overestimated the quality of the projector a little bit, but I think you can see the edges, right? Good. This is the algorithm. I paraphrased it slightly from the original paper in a compact form that allows me to explain it a bit easier, but if you look at the paper, you will see it. So we have 3 nested for loops, right? So the computer scientist among you will go, uh-oh, what are we doing here, right? And that, yeah, true. First step, let me simplify things a little bit, because for k is 0, then we can forget completely about this line. For every pair within the graph, where there's an edge between them, what we're going to do, we're going to see if they're independent. And if they're independent, we remove that edge from the edge set. Okay, this is basically faithfulness, right? I mean, if we see an independence, then there is no edge. We apply that directly. How do we do this? We start with, for example, x and y. We find actually that those are dependent. So the edge should remain. We cannot prune it. Before I continue, actually now pops into my head. I mean, I now use independent and dependent, just like this, like symbols, and I'm 100% certain that all of you have an intuitive feeling for what this would mean. But do you know how to measure, or how can we measure dependence, independence? How would you go about this? If I would now lock the room, right, and I would leave, because I have other things to do, and okay, well, I'm not going to allow you out, right, until you've come up with a independence test. And by the way, Wi-Fi is off and whatever, right? I mean, you can't ask ChatGPT. Yeah, come on, we're not going to make it too easy. How do we even measure if something is dependent or independent? What can we do? Mikael.
Check to see if probability of x given y is equal to probability of x, and also check to see if probability of y is equal to the probability of y given x.
That is pretty much the definition, but how would you do it in practice?
Well, you can do that by plugging into the data that you're given. So you would check for all the values of x where y is specific value.
Okay, suppose that we have continuous value data and limited, right? I mean, I'm not going to give you infinite data. I mean, that's I respect your time as well, right? Infinite data would take too much time. So I give you 100 samples of x and y, continuous valued.
In that case, probably assuming that they are numbers, real numbers, I can probably put them onto a graph and then see if there are any patterns where one affects the other instead of just being random, instead of the dependent variable being random noise compared to.
Okay, yeah. So yeah, intuitively yes. However, it's kind of difficult to put you into an algorithm, right? I mean, at the very least, we can't scale you up. so well, right? And you would have to look at stuff. And at one moment, I mean, not right now, but at one moment, we'll want to look at well, larger spaces. And at one moment, so if you go beyond 3 dimensions, it becomes very difficult for you to see stuff, right?
We measure the rate of change of one variable with respect to the other, condition on the other, basically. So if y is, if on the basis of x, y is changing too much, then there is a higher dependence, and if the y is changing less, then there is a...
Yeah, okay. Well, this is slightly more formally said what Mikhail said, right? So how would you do it? Does anybody know a test or like I'm not going to allow you out until you have something that does something, right? Max.
Something, but in the end, that would also boil down to estimating the probably the same issues.
Yeah. So well, if we would have discrete data, categorical data, mutual information would already be a pretty good step. Then indeed, also the arguments I had against your also disappear somewhat, right? Unless we have a very large domain, so very few samples, and then we have sparsity issues. But yeah, mutual information. Pearson correlation. Anybody know Pearson correlation? Right? Okay, that we could do. What could possibly go wrong? What is the bad part of using Pearson correlation? I'm not going to ask anybody to write down the definition, but hopefully you have still some intuition. Yes, go ahead, Pakar. Yes. So what does that mean? Yeah, but so let me phrase it again in my favorite way. What could possibly go wrong? Yeah. Exponential might actually, interestingly enough, work because, well, if it's exponential, then it will shoot off, and then, well, having some linear component, yeah, you will still pick up something. If let's say it would be sinusoidal, you will be dead because it's just flat, right? Even though there clearly is something going on. But indeed, so the main point is that if you use Pearson correlation or something of that kind, right, that is essentially parametric, that picks up one type of correlation, then yeah, if the true mechanism, if the F and the G's behind these edges actually have a different shape than you can pick up, you're screwed. Pearson correlation still works often remarkably well because even if the true relationships are almost never linear, almost all dependencies will have a linear component. You can very crudely approximate them. And of course, your statistical power will suffer, meaning that if you have few samples, you might draw wrong conclusions. Either way, right? But one other idea that you could just do is, well, let's regress x onto y and y onto x, and compare the regression errors to just a point model. And if x has some information about y, that means we can predict y better with x than by just, well, having y by itself, right? That's something we could do. That raises the question, which regression model would you take? Well, if you take a linear one, then we're almost squarely back to Pearson correlation, but hey, we can also do nonlinear things, right? Which ones and how and what, I mean, and so on and so forth. These are very crude basic techniques, right? I'm not planning to have a lecture on independence testing and stuff. There are very nice, I mean, kernelized methods that can pick up, even with low sample sizes, almost arbitrarily complex dependencies. I mean, pure theory, this is impossible, of course. You need large sample sizes, but in practice, the Hilbert-Schmidt independence criterion, for example, works wonders. Good. Anyway, I just wanted to quickly discuss because these symbols, intuitively you will get it, but how would you even do it, right? Okay, so this one we cannot prune, so sad. Then we measure between x and z, and lo and behold, that one actually is independent. So suppose we do my regression thing, right? I mean, I can't predict z better with x than just z by itself, so okay, no edge, right? I don't want the edge, gone. I do this for all pairs. And I do this entire exercise with the graph that we've come to know and love, right? That's the true generating graph, right? That's the one we want to discover. This means that if I now follow that graph, these are the edges I have left. So here at the top, here's a bunch that I could prune, right? But here in the bottom, yeah, then all of a sudden, because X and all its descendants will have some dependency, I can't prune that, right? And yeah, well, basically you get sort of like downward closure. This is how you can think of it a little bit. But okay, so that was the first loop of the algorithm. So let's now upgrade from k is 0 to k is 1. Well, again, for all pairs x and y in the vertex set that have an edge, and that is going to be the important part, that have an edge between them, right? So this is the edge that we try to explain away. Now for all sets of nodes, of k nodes, k is 1, right, that have an edge from x to that node and from y to that node. In other words, potential parents of that node, or potential, let's say, causal relatives. And if we then now have not just the plain independence between x and y, but conditioned on A, on the potential parent, if then all of a sudden becomes independent, we remove the edge. Basically, we're applying Reichenbach's principle of common cause, right? So in the first step, we determined, okay, is there an edge, right? And now we're doing the middle step. Can we remove the edge? Or do we have enough evidence? Now, in the example we discussed for Reichenbach, there was only one z. Obviously, there can be many z's, right? There could be z1, 2, 3 that together confound x and y. And given x, z1, 2, 3, then we can finally remove the edge. That is what this k is looping towards. It's basically the size of the parent set. But for k is 1, what can we do? Well, there we are. We start, for example, looking at x and y, because that one, I really want to get rid of this edge. Chinmay.
Similar, the dependency between x and y.
Yeah.
Is there an intuitive understanding to conditioning over the dependency? How do we?
It is, okay, so let me walk through the example, and then I'm going to ask you if it's clear, rather than trying to give an exact answer to what an intuition is. I don't even know if that exists, but I think it will become clear, right? So we have x and y. We all know that x and y, there's a true edge, right? We should not be able to explain it away, right? But the algorithm doesn't know that yet. So what we do is we take x and y, and we look at which other vertices have an edge to both x and y. Well, t is one of those, right? So we're going to loop over all, between quotes, t's, right? So we're going to do this for t, later for s, and so on and so forth. Not q, because q does not have an edge to either x or y, right? Okay, but right now we are here, and we check are x and y dependent or independent given t, which is effectively, we just take a value of t, right? Means red, and then we see are x and y independent, right? And we do the same thing for, okay, t is green, and so on and so forth. And if t is continuous valued, okay, then things become a little bit more complicated in the intuitive sense, but you probably can still follow. Okay, in this particular case, they're still dependent, so we cannot prune the edge. X and y, that edge remains right now. We try the next one, v in this particular case, because there's edges from x to v, y to v, so maybe v is explaining the edge between x and y away. Well, no, still not. V, still not. We cannot get rid of the edge x to y with just one parent. Maybe with 2 parents or 3 parents or 4 parents. We're not yet there, right? Let's move on, because we're in the loop where we're looking at parent sets of size 1. So now we just arrive at the edge q to w, right, or vice versa. Can we explain that one away? We take z as one of the parents because it has edges, and lo and behold, it's independent. Just like in the true graph, right? Because z was a common parent. So the dependence between q and w is only due to z and nothing else. There doesn't need to be an edge between q and w. So no causal edge, we can prune it. Okay, this is the general principle, right? Can we explain something away? In this case, with a budget of one other variable. If we keep on looping this, in the graph that I have, this is the next step where I'm left. So you see that I already could prune a lot of edges, right? It took me, of course, a number of loops to get that loops, like for every pair, every possible parent, and so on, right? But I can prune a lot. And this makes this algorithm actually, in practice, very, well, practical. even though, if you look at the computational complexity, it's exponential. It's horrible. It's relatively easy to see, because suppose that the true graph is the fully connected one. That means that in the first iteration, we check every pair. In the second iteration, well, we check every pair for every, and so on and so forth. So if this becomes a binomial, boom, right? In the limit, this explodes, right? For a limited sample, still, you can express it as a polynomial, but in the limit, this explodes. Good. Now, the moment that the true graph is somewhat sparse, that means, and sparsity primarily like, okay, what is the average number of parents that you need for a certain, let's say, for a confounded pair, then you have a very large pruning power already by, well, looking at parent sets of size 0, size 1, size 2. And the more you prune, the fewer candidates, because right now we are also done. I mean, I forgot to say this. We're done because if I want to explain away x and y, I would need 2 other nodes that are connected to both x and y. There's none. So I'm done. This one, no. This one, no. I'm done immediately. I never have to look at parent sets of size 5. If the true graph would be fully dense, then I would. So it is more of we need to put in the computation time often to exclude possibilities than to really find something. Good. This is what we call the causal skeleton, right? This was step 1 of the PC algorithm, or most constraint-based causal discovery algorithms, they work in a very similar way, right? I mean, and you arrive at the causal skeleton. What can we do? Well, we can apply orientation rules. You already know one, namely that of the collider. I call this rule 1, the collider. Effectively what we do, graphically depicted, we find structures that look like this, an A is connected to a B, B to a C, and A and C are not connected, right? Which, if we then observe this particular dependency, so A and C are strictly independent, but conditioned on B, they become dependent, then we already know from some slides back that the only way that that structure can come to be is if A causes B together with C, right? B is the collider. This is where the information from B and C collides. A and C don't know anything about each other, but if I tell you something about B, you know something about A and C, right? No other explanation. That allows us, and then I'll get to you, to find all of those structures. So effectively we measure this for this one, we measure it for this one, we measure it for this one, and so on and so forth, right? I mean, and for all where this holds, well, we can orient. So now we are at this graph. Mikhail. Then you misremember it. No, because this gives me the same conditional independences. It's only a collision, right? If 2 parents and 1 child, then the parents are independent, just like, well, let's hope that for all of us, the genetic makeup of our parents is independent, right? I mean, not, except for like common ancestors, I mean, from the cradle of humanity, I mean, thousands and thousands and thousands of years ago, right? So your parents are independent, but the moment we look at your genome, then, well, there is a dependence because your genomes carry something from your mom and from your dad. Only one explanation. You're the child of your parents, right? Or a freak mutation. But this is where we're always reasoning in infinite data, right? So the mutation can never be freakish enough. Yeah? Good, good. Do you have the intuition now? Yeah? Yeah. Good. So we now have this graph, right? This is what we call a PDAG, partially oriented directed acyclic graph. Is there anything more that we can do? Maybe. Let's see. Next step, so the colliders, we run this test once and then we're done, right? Because we can run this as many times as we want, but we're not going to find more colliders after the first run. Then there's also a second rule. I call this the no collider rule. The structure is that A causes B, and B and C not yet oriented, and A and C no edge. This is what we need to hunt for, right? This structure. And then we can reason, just from logics, that, well, if C would have been the cause of B, we would have already found it as a collider, but we didn't. Well, that means that there is one other possibility left to explain this generating structure, namely that B causes C. That's what we have here. That allows us to orient this edge, T2S. right? Okay, good. Now, not in this example, but you can imagine that by now having oriented this particular edge, T to S, there might be, if there's, let's say, another edge from S to not to Q, to R, I don't think we have R, then, well, we can just keep on looping this, right? And we do so indeed until, well, ad nauseum. In total, there are, give or take, 4 major rules. The first one, the colliders, we knew. The second one we've seen. And then rule 3 and rule 4, they're slightly more involved. But in the end, they all just apply, well, logical reasoning. Like it must be this because otherwise I would have seen something else that I would have been able to identify. So the no cycles one is easy to see. If A causes C, C causes B, then, well, B cannot cause A because we live in a DAG, right? So A needs to cause B. And effectively the same thing happens here. I call it magic because it's a bit more difficult to see, but effectively if B were to cause D, right, then we would create a cycle because this, D is not a collider between A and C, right? I mean, so there's no way that the edges from D to A or D to C would be going to D, which means they go outward, which means this one goes left, then this one up, and this one goes down again. But we don't allow cycles. So no, we do not allow the situation. That is the intuition of magic, right? Maybe not of all magic, but definitely of this magic. So there we are. Now we can orient part of our graph. The last 2 rules are useless in the example that I have. This is why I just obscure the graph, right? So we're just stuck with the graph as we had it, this one. Good. Not bad, considering that we started from, well, just having data. And with some assumptions, I mean, you can argue how reasonable they are, right? Do we live in a DAG, right? How IID is the data, and so on and so forth. But the fact that with those assumptions, we can now arrive at this, and reasonably efficiently so, cool, cool. Yes?
The question on the slide before, why couldn't we have A to D and C to D?
So A to D, D to C, A to D and C to D, because then it would have been a collider. Because ADC, well, there's an independence between A and C. I don't have an edge between A and C.
Yes, right.
So that would have made it clear. So I would have then spotted it here already. Yeah. But hence magic, right? I mean, it's sort of like a brain teaser. I mean, and I have to admit, every time I lecture this, I again have to look at it, okay, how does this work again exactly? And yeah, but it's also, I mean, it's quite obscure, right? I mean, the first 3 are the ones that orient most. If I remember correctly, Rule 4 was also proposed, I think, in 2018, relatively recently. Maybe it was 2008, I don't know, right? I mean, I might be off by just 10 years, but still, I mean, for such basic rules, yeah, it's not going to all of a sudden increase the performance of your algorithm from abysmal to superior, right? I mean, it's just one little delta. Yeah, good. So far, so good? Constraint-based causal discovery? Yeah, good. Now, what I'm not going to be lecturing about are methods from the FCI family. This is fast constraint-based causal inference or causal discovery, which allows us to determine not just oriented edges like we have here, but also determine, like, for example, this edge here. Say, like, well, I can't tell if X causes Y or Y causes X. And we don't have a confounder that I observe that explains it away, but somehow I find this very suspicious. And then you get, well, some dots over the edge, basically saying, okay, I think there is a hidden confounder. And well, based on the theory, that is then often true. There are a few exceptions, but the Verma rules and whatnot. That is the FCI family. And you have generalized and whatever GFCI. I mean, there's a ton of algorithms in the FCI family. The core of it is very similar to PC. So that is the part that's well, you need to know. Let's move on to the second main class of causal discovery methods. This is from 2002, the algorithm at least. It's called GUESS, for greedy equivalence search. I have no idea if Max Chickering have a sense of humor, because I find guess for a algorithm that, well, tries to get something. I find it delicious. I find it delicious, but I have no idea. It could really be okay. I just have my acronym. Okay, it's guess. That's it, right? You never know with computer scientists and statisticians. But, okay, so guess works very differently than PC. And I would say that maybe because my heart is more score-based and constraint-based, I find it a bit more natural, but yeah, your mileage may vary. What do we assume? Very important, always to check this. Data-generating distribution has the causal Markov property. Okay, check. Faithful, check. Only one graph, check. All relevant variables, check. And IID. Hey, that looks very familiar to PC. Maybe because Max took a bit of inspiration from the PC algorithm, right? And I know that in these conditions things are going to work, so let's not deviate too much, right? Also has two main steps. I'm not saying that this is necessarily the, let's say, taking inspiration from PC, but what are we going to do? Rather than starting from a full graph and trying to prune edges away, explaining things away in Hans Reichenbach style, we actually do the opposite. We start with an empty graph, and we're going to iteratively add edges that help us to explain the data better and better and better and better. That's the main idea. And we do this while maintaining a PDAG. So we're not maintaining a DAG, but we're maintaining a PDAG, which live within a Markov equivalence class, hence the E of guess. Now, as you can imagine, if we're adding edges, we might add some edges that, well, we actually don't want. For example, if through whichever, let's say, so if Z causes both X and Y, right, and X and Y have, let's say, smaller domains, it may actually be that the first edge you want to draw is between X and Y because they explain each other so well, right? And the mechanism from Z to X and Z to Y is more complicated. I will add it later. Well, that would leave you with one edge that you don't really want. Of course, once you have the correct edges from Z to X and Z to Y, you don't need this edge anymore. You can already explain X and Y perfectly well from Z. The simplicity is not really favored anymore. So this is why in the second step, we're going to do a backward search in which we prune edges, right? So first add all edges such that we maximize effectively likelihood, then prune such that we maximize likelihood under a regularizer. And well, if we do this the right way, we can prove, Max could prove, that we actually find the correct causal graph. So the main idea of guess is super simple. The theory is a bit complicated. I'm going to make an attempt at explaining it. Maybe I succeed, maybe I fail. You'll be the judge. Guess starts with the PhD thesis of Chris Meek. And Chris Meek, in his PhD thesis, well, there was one thing that he couldn't prove. So he was working on structure learning, Bayesian networks and whatnot, and he had a conjecture. And conjectures are fun in the sense that, well, you sort of leave the burden of proof to somebody else, right? And in this case, well, Chickering 5 years later did that. But basically what Meek said is that if I have a true graph, G, right? And so the notation is here a bit screwed up, at least in my in my view of the world. So we have a true G, and we now have an independence map of G. And an independence map means that on my map, G star, if my map says that, no, if the true graph is independent, right, two edges, there's no edge, then in my graph there should also not be an edge. So I can basically look up in one way. Right? A completely empty graph is also an independence map of the true graph, because I at least have all the correct independences, right? Now, after each edge change, flopping around, adding edges, and well, yeah, so that's adding edges in turn, right? And then there is actually a path from my independence map to the true graph. By just adding an edge, adding another edge, under certain conditions, flipping directions of edges, I can walk through the true graph. Feels a little bit trivial, right? Because if we start from an empty graph and you will want to arrive at, let's say, a chain from A all the way to Z, yeah, just add an edge from A to B and B to C and so on and so forth, right? But of course, you need to reason within a certain score and how you're actually going to do this. And this is what is swept below the carpet. So effectively, what it came down to by Meek's rules, following from the conjecture what he based it upon, single edge additions. So we just add edges. and we have covered edge reversals. This is basically the types of edits that he allows. So here, if we have parents that, well, cover these, right, I may flop this edge around. Effectively, this is based on, again, if we look at these edge orientation rules, it could be this, but it could also be that. So you know what, I allow you to flip things around. And that allows me to initially make a mistake and later fix it again. That is the general idea. And after all the changes, if we did everything right, then we arrive at a true graph. Then we're happy. Now, it is great that such a chain of steps exists, but how do we choose which step to take at what moment? Who knows? This is where Chickering comes in. He showed that if we use BIC, the Bayesian information criterion, as a regularizer, then, oops, let me stop this distraction. And effectively, what does BIC do? That penalizes having, well, additional edges that we don't need, spurious edges, right? And we use this with an appropriate, between quotes, likelihood estimator, effectively one that is consistent, meaning that the true graph in the limit of infinite samples is going to get the highest likelihood. Basically, we really apply the principle of maximum likelihood, right? That is effectively what this proof all hinges on. Then we can actually discover, or we can identify the true causal graph. You can also, if we now drop BIC, and I still have an appropriate likelihood estimator, I have a problem because any supergraph of the true graph, even if the edges, right, I mean, so I would do the coefficients, I would tune them to 0, right? I mean, the edge is still there, right? So I want to get rid truly of the edges. So I need a mechanism to get rid of edges of coefficients I don't want. This is where BAC comes in, right? Because that really puts a penalty on each edge, and if, well, no matter if the true coefficient needs to be super small in order to get some likelihood contribution, well, in the limit over many, many samples, that contribution is going to be more than the penalty that BIC implies, so BIC is, well, helpful there. This is the core argument of Chickering. Good. Now, one other aspect here is that, let me see, where should I put this? The appropriate likelihood estimator, one of the appropriate aspects of it in order for the algorithm is that it's, well, equivalent. Equivalence is required, meaning that if I have A and B, and let's say, well, then there's an edge between them, right? And let's say that we know it's actually A causing B, but these two, what Chickering explicitly wants is that you have a score that if I condition A on B, and I also have then a score for B alone, or I do the opposite, we get the same score. It's very important that, well, we get equivalence. It's not that you all of a sudden favor A to B or B to A. No, we really want to apply standard probability theory there, standard factorizations. That allows to search over Markov equivalence classes relatively efficiently, rather than having to look at over all possible DAGs. So it saves you from exploring an exponential search space, but at the same time, yeah, you leave the back door open in the sense that the monster of only being able to discover Markov equivalence classes comes in. Namely, we cannot orient all the edges. For that, you would need an inequivalent score. But with an inequivalent score, the guess algorithm doesn't work, or it's not guaranteed to give you the correct answer. So the idea, the basic idea, which I illustrate here, is really from an empty graph, greedily add that edge that is not yet in the edge set, that maximizes the likelihood, well, that we have from the data given the graph. So in this case, it could be x to y. Note that I add an unoriented edge because, well, I just choose one of the two, right? Either x given y times p of y, or the other one, equivalent. You already see that it saves me a lot of computation. I don't need to look at all possible pairs, right? I just need one sample from the Markov equivalence class, and that's that. That speeds things up. It also allows me to search then over, well, max Markov equivalence classes by for example, this edge over here, if I were to, or let's say this one, in the next step, I would add this one, right? What I do from this graph, I contemplate every possible edge that I could add. Good. But I don't need to compute for all of those, all possible orientations. Because obviously, if we now consider this edge, do I consider x to y, y to t, which has a different meaning than y to x, y to t, because then y is not explained at all by x. And it especially becomes more apparent if x causes y and t causes y, because then together they will really explain much more of y than just x by itself. So there you can already feel that actually to get the true likelihood, if you wish, using the true mechanisms, you cannot do this with just equivalence. So this is why this notion of requiring equivalence sweeps things under the carpet, because you abstract away from the actual SCM and you move to a non-parametric plane where it's just really edge existence. This is what we're reasoning about. But the effect is that we can just contemplate every individual edge. We can compute these scores locally, so it speeds things up massively. The moment we arrive at, well, actually we should already do this here, but if we have a structure like we've seen before, we can test, is y a collider? Because if y is a collider, well, then we should, of course, orient these edges, right? But otherwise we can't. Here, between yq and t, we check for a collider. Yes, it is. That is now the mech from which we then expand again, right? So that basically shrinks the space of possible extensions, because we don't allow for cycles, for example. This way, we arrive at this graph. We apply, for example, we arrive at this graph. This is the forward stage. Maybe we would have oriented a few more of the colliders. Doesn't really matter in this particular case. You understand the principle. But this is the forward phase. And then we have the backward phase. And there we consider again every edge that we have, oriented or not. And one by one, we take them out. And we see if this improves the regularized likelihood. So in this particular case, there should not be an edge between Q and W, right? This is really a remnant of Z confounding it. Taking it off, it costs perhaps a little bit of likelihood, but that is compensated by the gain in the BIC penalty that we now don't have to pay. So there we are. This is how guess works. Simple, greedy algorithm. It's a bit of a pain in the neck to implement because you have to search over these mechs, right? But well, once you've got the main idea down, all is good. Okay, any questions? Because I realize this part is less, let's say the intuition is equally easy, but the details are a bit more murky than for PC, but no, are we good? Good. Then I'm going to quickly explain continuous optimization-based causal discovery, and then we're going to have a short break, and then we continue with, well, the second part of this lecture, and that allows me then 5 minutes to think about what am I going to lecture exactly about, because I have both the remainder of this lecture and some things that I can chip in from last week, because for me it's also a whole new world that we're now sort of halfway already at this point. A few years ago, roughly with the no tears paper, so DAGs with no tears, that's the title of the paper, 2018. Up till then, structure learning and specifically causal discovery were really combinatorial based. Just nobody even, I mean, well, some people have thought about continuous optimization, but it all failed miserably. Then Zengenel in 2018 proposed a no tears algorithm, and you could say that took the world by storm. Now, there's a few things to be said there, but I respect these authors very much. And now you might expect a but. No, I respect them very much because, another B word, because in their paper, they are very clear they are not doing causal discovery. They're doing structure learning. And you may ask, okay, what is structure learning? Structure learning has, in a way, the same goal as causal discovery, namely, given data, find causal, or not causal, strike causal, find a DAG or a PDAG, right? That is the goal. But they don't have the guarantees. So you should not claim that it's causal, right? They are living on rung one. They assume certain things to make their algorithm possible. So maybe they're in rung 1.5, but you cannot prove for their theory, for their score, nor for the method, how they optimize, that the result will be at rung 2, which for guess and for PC is different. There we really formally prove this is the only explanation, not just an explanation that happens to fit the data well, and if you cross your fingers, then maybe it is causal, right? They are very clear in this. Pretty much every paper that builds on top of this, they say, okay, well, Zeng et al. Said it's causal discovery, and they show identifiability, which they didn't, and therewith our method is also identifiable, which I don't agree with. So there's no guarantees for consistency in the sense that in the limit, their score may or may not point out the correct causal graph, right? Or identifiability in the sense that the model that they assume, if I give you infinite data, is it even possible that only one such a model generates this data? This is something we'll explore again in some time. Again, two main steps. They assume a linear model. So the world is not just a DAG, but it's also a linear DAG, right? Because they need to optimize something. They enforce sparsity, and they don't do this using BIC, but they take a L1 with some lambda, some hyperparameter, right? For how much do you weigh this? This is already where you can see that the consistency is sort of out of the window, right? Because the key thing with BIC is that you can prove, because of the logarithmic nature in the type of sum, that it basically vanishes, right? I mean, it gets completely dwarfed by the likelihood term. Here, no, just there, depending on how you choose lambda. If you choose lambda right, maybe. If you choose it wrong, maybe not. How do you choose lambda? Nobody knows. And in order to get a DAG, of course, the graph needs to be acyclic. This is the main innovation of their paper and the one that I like the best. What they do is they look at the Hadamard product of the weight matrices, well, the exponents of that, and they take a trace, and they show that under these conditions, a DAG arrives at 0, it witnesses 0. So to use this then as a regularizer basically means that you push your neural network when it learns it, because that's effectively how we can think about it, right? I mean, that we have a weight matrix, and we tune all the weights using stochastic gradient descent or some other, I mean, that I don't think you should use a convex optimizer here, but you catch my drift. Step by step by step by step. Then in the end, we arrive at a weight matrix that looks very good as a DAG. In this particular case, it will orient all the edges because, well, we just choose the variable with the lowest variance as the parent. There, by now, you should also have some intuition, like, okay, yeah, I can see why they do this, but you should also be like, but wait, what? What does this mean? What could possibly go wrong? Because variance, it feels natural that variance increases, but if we project a large domain into a small domain, yes, or actually no, right? I mean, then all of a sudden we're screwed. I mean, from small to large, yeah, that is fine. We get probably larger variance, but the other way around, no. So it means we have a very strong implicit bias. So the orientation is not consistent, and the score as a whole, neither. However, I'm not going to bombard you with plots for how amazing it works. You do get very good graphs with no tiers compared to many of the other algorithms. And the other algorithms, you can, well, actually, let's play the game before we have to break. What type of graph would you expect the PC algorithm to not like? And not like in the sense that, well, not so much in, let's say, computation that we already discussed, right? But specifically, if I give you a limited sample, 100 samples, 1,000 samples, right? I mean, let's keep it real. Let's not go to billions, right? I mean, that's you may tinker with the number of features that we're reasoning over, as well as with, well, the structures and how they are connected. Which graphs would you guess would PC struggle with in practice? So which structures will it difficulty detecting? give everybody a second more. But so let's recall, right? So, or let's walk through it step by step. Let's say first iteration of PC, finding, well, all the pairwise dependencies. Is there any reason why that step would be in pain? No, unless, well, of course, the true data generating mechanism is, let's say, sinusoidal, and we use then a PC or something like that, right? I mean, okay, but let's not play games like that, right? So first step, no. Second step. So we now need to find potential parents for every edge that we don't have explained yet. Okay, for one parent. So now we need to compute conditional independences. What does that mean in the amount of data that we need? If we go from unconditional, marginal dependence to conditional dependence. How much more data or less data do we need? Can we reason about that? Let's make X and Y binary. Actually, all variables are binary, right? X and Y are binary, Z is binary, or Z 1, 2, 3, 4, 5, right? And that. In order to determine that X and Y are independent or dependent, effectively what we need to do, right? If we use mutual information or any of its friends, right? I mean that, let's say we take Rényi entropy of, is it then 0 first? I don't know. But effectively it comes down to counting. How often do we see X take the value 0 and Y take the value 0, respectively 1? And same thing for X is 1, right? And then, well, if this is completely uniformly distributed, they're not dependent. That's basically the statement we would like to, right? So if I give you 1,000 samples over X and Y, well, then given that there's 4 possibilities, 0, 0, 0, 1, and so on and so forth, right? That is probably enough, right? That's probably enough. Now, how do we determine now a conditional independence? We now also have a value for Z, which is again 0 and 1. So what we need to do is for all records in the data where Z takes the value 0, we need to count how often do we see X and Y being 0 and 1. So effectively, we halved the data that we had, right? Okay, given that as I gave you 1,000 data points, given 500 data points, you can determine X and Y still quite well. Okay, now we have 2 parents, Z1 and Z2. What does this mean? I again halve the data you have. And again, and again. And very quickly, you run out of data, right? It's not that you need only 4 data points to determine if X and Y are independent. We need quite a bit more. What the actual sample complexity is of the test that you're applying, that remains, well, a mystery unless we really look at the test. But the more conditioning variables, the more PC is having a nightmare. Or actually your conditional independence test is having a nightmare, right? This is where that really goes wrong. So a situation, a graph where we have many parents and only limited samples, yeah, we're kind of screwed. Actual implementations of the PC algorithm, they typically restrict the number of parents to 5. Just like physical, but implementation. Beyond that, it's like, well, given that you need an exponential blow-up, like, okay, don't even bother. Right? And of course, we were now talking just about binary data. If we're now thinking about continuous value data, you need to estimate distributions, right? Which of course for binary data is relatively simple to do, but yeah, there you see that many parents, bad idea for PC. Can we reason similarly for guess? Can we think of a scenario where guess is going to have, well, a bad day? Or let's start with the same scenario. We have now some variable with 7 parents, right? So PC, well, the standard implementation would just not even find it. Does guess have the same problem? Anybody want to wager a guess?
I think it doesn't have the same problem because we really add only those edges and then it's so local. It's much less responsive.
Yes, yes, exactly, exactly. So there, it doesn't really matter, right? It will just grow its way towards it. What are we secretly then assuming in this? It grows its way towards it. Yeah.
Adding edges that are known well. Because it could be explained way by the already.
That is possible. That is possible. It's a good point. That's a good point. Not what I had in mind, but I mean, that's a good point. What I had in mind is more that it might be that if I give you x and its 7 parents, this entire graph, like, yeah, this has great likelihood. This is conditionally independent. You're super happy. But, and well, PC might still have too little data to determine the independences, right? So it might not be super happy, but okay, fine, right? But for guess, what we're effectively doing, we're assuming that we now can actually add these edges one by one by one by one, meaning that at every step, the increase in likelihood that we have by adding an edge is, well, outweighs the penalty that we get by BIC. And with many parents, you again have a bit of a problem because how much is the likelihood going to increase? If it is truly an independent mechanism, so effectively X is a bit like with the wet grass example, right? I mean, so we have one function, another one, that really explains different parts of X, as to speak. Sure, that probably works. But if it actually is a function, a complex function that takes seven variables as input, then who says that if you take only few of them and only have the partial function that we actually get enough likelihood? It's really one of those things where things may only be obvious once you know it, once you see it. So also guess doesn't like many parents. Does no tiers have this problem? In principle, not. In principle, we start with some random weight metrics. And as long as this, well, nothing is at 0, right? Because that's a bit difficult to gradient your way up again. But if I already have all the influences and I just, each step, I just tailor them a little bit, one step at a time, rather than really having an edge or not having an edge. And when you have the edge, and you also need to reason about the parameters and how to make them good. No, we have all of them a little bit, and we can sort of wiggle our way to, well, a graph that looks quite well. That's one of the strong points of no tiers and friends. A big downside is that it's not causal. And one of the other big downsides is, and this is where things can become a little bit convoluted, these continuous optimization-based methods, they are in theory very good for large input spaces, right? This is what neural networks are great for. But in this type of learning, they kind of suck. Because W becomes, well, a very big matrix, and we again need a lot of data, and typically these things only work for relatively small feature sets in practice. Good. Let's have a short break. It's now 12 past. Let's have a, well, after I answer Max's question or query, let's take a 5-minute break, and then we continue for a bit.
But it seems that this L is some score that determines the quality of a current graph.
It's a linear model. It's the fit of a linear model.
Yeah. Why can we not also like combinatorial optimization on the whole graph?
We could, but then we lose the consistency. So it's basically, you can do this, but guess has guarantees. It's okay, we don't want the guarantees. Yeah, sure, you can plug something in. The idea is not bad, right? The idea is really that, okay, well, a linear model, right? If you believe that we live in a linear world, sure, then we can fit a linear model. And then rather than just taking the crude fit, right, maybe we can make this a bit more probabilistic, and then you get the properties in guess. So you can definitely instantiate guess for linear models. And in a way, guess even likes linear models for reasons that we will see soon enough. Yeah? Good. Let's reconvene 20 past. Let's take a 7-minute break. I think this is fine. Yep, good. Good. So it's 20 past. I'm gonna give you a choice. I can either continue for a bit, discussing some of the, well, what could possibly go wrongs, I mean, two specifically, for the methods we've seen before, not specifically this one, but actually specifically for constraint-based. Actually, no, that's for constraint-based and for a score-based. You can use it for both, I think, in both cases. But two, let's say, non-trivial fail cases. That's one option. The other option is that we start thinking about how can we go beyond Markov equivalence? How can we go beyond finding just merely this partially oriented DAG? Asking the question, how can we orient, well, the rest of the edges or all of the edges? That's a bigger topic, which normally I would start next week, but we can make a start today. It's not a problem. It allows me then to put in some other stuff that actually also naturally fits in next week. So those are the two options I lay before you. First of all, who is awake? Okay, most. I mean, Magnus is not awake, apparently. You put your hand like very quickly down. I'm with you, bro. I'm with you. So who is more interested, if you have a preference, in looking into failure cases and how to fix them? And who is more interested in orienting the rest of the edges? First, for the failure cases. No preference. One preference. Okay. One. Good. Edges. Okay, more. Okay, good. I'm sorry, Chinmay. I might squeeze it in somewhere at one moment, but oh, okay, good. That's been. Whoopa. So then I just need to quit this. Oh, yeah. Need to reorganize Zoom for a little bit. Slideshow from current slide. Share. So, good. So, well, back to the question. We now shift gears a little bit to how can we measure causation? And the goal is still discovering, but somehow we now need to determine, given two variables, does x cause y or y cause x? This is not really the discovery of an edge, right? It's more like what is the shape or the direction of the edge. This is what we did just ago. We know that we can arrive here, and this is what we would like to solve. What are the directions of the other edges? Now, in all of the previous, the way we could orient edges is basically using a third wheel, a third variable. In order to determine the direction between A and B, we need C, and then in special cases, we could use it, right? But because the factorizations between just two variables are exactly the same, and there is no variable that we can condition on, we don't have that luck with just two variables. So for a long time, people said, okay, this is just impossible. Can't do this, right? I mean, not with guarantees. These are also the people from the camp that say, well, we want to do causal discovery, causal inference, as non-parametric as possible. And you might, well, now see immediately that what I've been discussing about PC and about guess, this is all non-parametric. We were not talking about specific shapes of the functions. Right? The moment we instantiate it with Pearson correlation, sure, right? But that is exactly what we didn't want to do. With the ultimate independence test, this doesn't happen. So we want to now look into this one. And the non-parametric people were right, in a certain sense, that this is impossible. However, if we are already making assumptions about how the world works, adding a few more might not hurt as badly as, well, the first one, right? The first cut is the deepest. So effectively, we're looking into this case we started off 2 weeks ago. Looking at the definition of causality, and I had it there for a reason, because everything is connected, of course. The relation between something that happens or exists and the thing that causes it. Okay. Now, with that in mind, and with the do calculus in mind, we know that if x causes y, and we do something to x, we will see something in y, right? So the way that I put it here, if we wiggle x, we will see y wiggle, but only if x causes y. If we wiggle x and y doesn't do anything, and the other way, so basically we cannot wiggle x by wiggling y, right? It's one directional. This is of course assuming that we live in a DAG. If x and y are interacting with one another, so let's say this is a gene regulatory system and the one upregulates the other and downregulates, then well, this up will go, then wiggling the one will wiggle the other no matter what, right? But we don't live in that world right now. The key idea of a randomized controlled trial, and you will not think of it as wiggling, because, well, we're not changing, let's say, the dosage of a certain drug for every person differently at every moment, right? I mean, that there are some, this is why there's ethic boards, I guess. But in a way, this is how you can think about it. In observational data, we cannot do the wiggling ourselves. And you might then reach the conclusion, there's nothing we can do. Or is there? Here, I've gathered some data. I see Max smile. Max recognizes the data, I think, right? I gathered the data a few months ago, and then I already showed it to Max in a different course. And I gathered this data. Actually, I sampled this from the function that you see, right? But if I were to give you this data, you would probably also learn this function, would have drawn it very similarly, right? Now, I'm not telling you if x causes y or y causes x. I ask you. And Max may not answer yet. What would you say? Does x cause y or y cause x? And I'm also going to ask why, right? I mean, I'm pretty certain that everybody can just randomly choose one direction, but why? See, now it's dangerous that I know your names. Because now I can say, Elina, what do you think? Why? Yeah, continue. I like the direction that you're going, or at least there's potential. Yeah. Okay, now I don't like the direction that you're going anymore. Sorry. Okay, yeah. See, Florian. Your name I already know. I'm sorry.
Just thinking, I'm trying to identify, just think about y and then what exactly happens in x and what is weird about it. If I move y, and that one place where it goes to the right, would that be
Here?
like
Or here, you mean, or where?
yes, or the lower plateau?
This one, yeah.
Would actually mean that if I change something in y, it would like in that certain area would move x and like greatly basically,
Yeah.
and that feels odd.
That feels odd, yes.
So I
Okay.
would say x, y.
Okay. So you could also say that, well, here in this area, moving x a little bit moves y a lot. So is this then the argument in the opposite direction?
Which doesn't know.
If I change x here a little bit from left to right, so look at the curve, then y will go up quite steeply. Is that what you meant, or did you mean something slightly differently? So is it the steepness of the curve that you're concerned with?
It's not really the steepness, and I'm not saying that it's like a change, but it just feels like it's almost flat. So it would be like I mean, is it, let's say it was even going down again.
Yeah.
It would mean that I have two possible values for a certain y value.
Yeah.
Explain that.
Mm-hmm.
I couldn't tell, all right, what am I getting for the x because it's not a function anymore in that sense. I don't know, that's your question.
Yeah. Yes.
Not
Yes.
x.
Yeah. Okay. That's. Of course, I mean, this function is still monotonically increasing, right? So,
It still is.
but so there. I mean, I see where you're going, and I would say you're on the right track. Not there exactly. Has anybody read the title of the slide? I mean, no, right? Yeah, I was elected to lead, not to read, right? That's that idea. Yes. Okay. Now that you've read the title of the slide, does x cause y or y cause x? And why? Okay.
Read that on slide, I think that x causes y because if y caused x, then I would have expected the noise to look different in the way that it would be more varying from line in this direction rather than more even varying in this direction.
Yeah. Okay. I think you're on the right track, but it's not really crisp yet. But we'll get there. So what is weird, and I think all of you saw this and triggered on this, but didn't really know what to do with it yet. That indeed here you have this plateau or very steep area, right? Well, it's not so much the steepness or the plateauness even, but we have here a value of y with a very large entropy, wide range of x, right? And actually a large density of y. If we project the points that we have onto y respectively x, right? What does it look like? Let's do that. Forget the text on the right-hand side. That I actually get this weird bump here, right? In the density of y. Whereas x is nice and flat. Right? Just go back, you'll see I can dump it down, right? And I can flop it to the left. This is the shape that I get. Well, it's not that I like one shape better than the other per se, but it is of course a little bit weird that where y is dense, this correlates exactly with the steep part of x. So namely, what we then essentially get is that the noise, so we have some function, right? I mean, that's f to y we can contemplate. And this has this shape, right? But in this part, all of a sudden, the noise is much higher. Exactly where it's steep. And then when it's flat again, then we get very low noise. And now it gets high again. So the noise, which you, well, intuitively would expect to be independent of the true mechanism, at least to a certain extent, right? Heteroscedasticity is a thing, but fair enough. Whereas in the opposite direction, x to y, we don't need those shenanigans. In the x to y direction, we have a function plus a Gaussian. The width of the noise is the same everywhere. And I think, Elena, this is what you were hunting for. And then you flopped. I think this was where you were going for, right? But lacked a bit the precise words, I mean, not holding it against you. Because this was discovered, well, this plot is from 2012, but the idea is from 2005, 2006. So, sure, 20 years ago, but not that ancient either, right? No. And what you were saying goes in a direction, but yeah, not really looks at its entropies. No. So the moment that the structure of the density and of the function, if they start to correlate, that is weird. I need to have an explanation for that. And of course, it might be that if my machine gets, the hotter it gets, the more noisy the readings are, right? Stuff like this can happen, right? So sure, it may correlate in certain ways, but I need an explanation. Without that, without this explanation, I would rather go for saying that x causes y than y causing x in this particular case. And the way that this data was generated is indeed, this is correct. Yeah. Many slides have good titles, right? I mean, just pay attention. Just this one, it was just there. I've even contemplated really just x causes y and just seeing if people read it or not. But yeah, I don't want to rub it into your face that much. Good. Okay. This leads us to what is now known as the principle of independent mechanisms. The idea is that if x causes y, that the marginal distribution of the cause, so the one that was at the bottom flat, right, I mean, and the conditional distribution of the effect given the cause are independent. So all information is being transferred through, well, the mechanism. This is the py of x, right? So or let's say the f of x that results in y. And whatever noise you have left, that is this, right, should be independent of the marginal of the cause. It's exactly what we saw previously, right? This is the formalization of this intuition. So if the distribution of x contains no information about the distribution of y of x, of y given x. Okay. Previously, I asked you, how do we measure independences? How do we measure this? Because it's a cute intuition, and we already saw an example, so we can conjure up some method that roughly does it, but how would we do this properly? One way to do this, and this is then the paper by Shimizu, 2006, and that set in motion a whole long line of research. They were the ones who noticed this behavior that we just saw for the first time, and or noticed and acted upon it, in the sense that they formulated this model, the additive noise model, and they reasoned about it. What would it mean? An additive noise model is very simple. If this is the true generating model, so y is really a function of x plus noise, where the noise is independent of x, independent of the input. It's exactly what we just saw, right? We just get this nice Gaussian band around the function, and the function can be, well, at least in this definition, anything, right? Note that here the noise also doesn't have a shape specified. So I know in the example it was a Gaussian, but we can also reason about other things, right? Now, if we generate the data in this way, and we can show that in the opposite direction, so that it is impossible that to fit a function g of y, and the noise that we then have is independent of y, but still reach x. If that is impossible, well, then we have identifiability. Then under the assumption that we live in an additive noise model, right? The data was generated by an additive noise model. Well, there's only one direction where we can fit it that satisfies, the other one not. Okay, well then the one direction is the causal direction and the other one is not, right? Very simple. Let me see, what do I have here? Yeah. Let me go a little bit off script. How would we do this? So now we can make this assumption that we live in an additive noise model, right? I give you data over x and y. Peter Spurtus and Clark Glimmer say, I've got no idea what to do. Max Chickering runs away scared, right? And that's what with this, right? Armed with the insights of Shimizu et al. What could you do? Ashraf, what would you do? Sorry? No idea? So data was generated like that, right? You don't know it yet, right? That's so. But we assume it has this form. We don't know if it was x to y or y to x, right? That's what the question is. So what could we do? Chime, do you have an idea? No?
So we have to identify.
I give you data over x and y. Your task is to tell me x is the cause, respectively y is the cause. And being the generous God that I am, I tell you, yes, this was generated by an additive noise model. I forgot which direction.
By this logic, if I add noise to it and if the noise changes y, assuming that noise is independent to x, and if the noise changes y, then x is causing y. And if the noise does not change y, then we have to test for the other way around.
You're thinking a bit too convoluted. It's quite simple. What we can do, we would need to make some assumptions, right? And that, let's live in linear land again. right? Or let's not let's do polynomial nonlinear regression. Let's spice it up a little bit, right? But still, EML. It's it third lecture. What is it? So I give you data over x and y, and we fit a model. We just regress x onto y, right? That gives you an f. We can also do it in the other opposite direction. We get a g, right? For those, we also get some residuals. Well, those are n and n tilde. Okay, what do we do next? We need to see, does that hold? Are n and x independent? Respectively, n tilde and x independent? Well, let's use Pearson correlation for that. Right? I mean, really, we're torturing this data, right? I mean, it's crying for its mommy, right? But I mean, let's just do stupid shit here, right? Then in the causal direction, what would we fit? We would, given enough data, right? I mean, Gauss-Markov theorem and whatnot, we would find the correct model, f. In the true direction, it is truly independent. So it's only if we fit the wrong model then it would make it dependent, but there's no reason to do so. But in the opposite direction, we know that in an additive noise model, it is impossible to find a function g and noise n that are independent. I'm going back a few slides. From x to y, I can find a function f, this squiggly thing, and noise n, right, for x, which is just this Gaussian, just a simple, cute little Gaussian, right? That's it. Whereas in the opposite direction, sure, I can find a function g, that's the inverse squiggly here, but the noise that I find, the n tilde, is not going to be independent of y. Because for these values it's low, and for these values it's high, and now it's low again, and now it's high again. We have a dependence. It's borked. So for this data that is truly generated by an A&M, it is impossible to fit, under certain conditions, this is where we go next, an A&M in the anti-causal direction. You can only fit it in the causal direction. So effectively doing regression in the one way, the other direction, in the other way, and then looking at the residuals compared to the inputs, right, allows us to determine if the one direction or the other direction is independent. Now, mind you, we have instantiated it very crudely here, right? Using whatever polynomial regression and whatnot. So, of course, if the true f is not in the family that we're trying to fit, we're screwed. What type of noise are we fitting? Well, in regression, well, it's basically sort of we're forcing a Gaussian. If it's not truly a Gaussian, then we might actually find the wrong. So it was very crude, right? I mean, it was not neat and nice, but it gives us a general idea of how to approach this. Also, how did we now measure the dependence or independence between the input and the residuals? Pearson correlation. Not really great either, right? We already discussed that. So we also need something smarter there. But the basic ingredients are there, right? You could now, if I would lock the room, right, again, I'm horrible, you could get yourself out of here relatively quickly. Good. This allows us to infer x towards y. Now, up till now, I said, okay, well, if this is the true model in the one direction we can find it, the other direction we can't find it, then we can draw this conclusion. But, well, I didn't say anything about the shape of the function yet, about f, the true f, or the shape of the noise. And, well, maybe A&Ms are identifiable for any combination of functions and noise, and maybe they're not. This is something that, well, we would need to study. This is exactly what Shimizu and Hoya and whatnot, what they looked into. Let's walk through this. Suppose that the true generating function, right, the true f, which I know, you don't, is linear. And the true noise, n, is Gaussian. And the true noise is Gaussian and independent of x, right? I mean, so the true A&M, linear and Gaussian. Is this model identifiable? Meaning that in the true causal direction, sure, you can fit it, right? There you can get this independence. But now the question is, in the anti-causal direction, do we have the case that it is impossible to fit the model? So it's always dependent. That is the question. So for linear and Gaussian, we make f linear and n Gaussian. What would happen in the anti-causal direction? Jimmy. Okay, so if I'm going to do like this, right? And that's towards the camera. So this is our axis system, right? F is linear. Let's just make it diagonal. You can change the slope, right? Okay, and then I add some noise around it, Gaussian, right? So we have a band, right? That is the causal direction, X, this is Y, right? So in the anti-causal direction, I would say this is still pretty damn linear, right? So, okay, G is also linear. What does the noise look like? Does the noise have a special shape, or is it equally uniform in a way, the shape, as it is in the causal direction? No, go ahead. No, go ahead. So effectively what we get is that if the true F is linear and the true N is Gaussian, then effectively we have a band like this. This means that, well, G is just the inverse of F, still linear. And the noise, the stupid thing about Gaussians, them being symmetric, rather than being like this, we get this. And perhaps with a slightly different variance, that depends of course on the slope. So if the slope would be really 45 degrees, then, well, we even have the same variance. If I make it more flat, then okay, I get a larger variance in the opposite direction. But unless you say, well, I know that X causes Y because the variance of the noise is lower, right? This is the world that I live in. Yeah, fine by me, right? I mean, then we can do causality in your world. But in my world, I'm not willing to make that assumption. It's also not what A&Ms assume. A&Ms assume the independence. That basically across the function that basically the same noise is being applied and not all of a sudden different shapes appear out of the wild, right? Out of nowhere. So Florian, I think you wanted to add something, but maybe I already said what we...
No, I had a wrong idea. I thought the variance was actually different for the lower part. Like if you flip it, that you would have like rotated Gaussian. But actually, I realized that it's just...
Yeah, and that's why this in 2006 this was not a trivial. Wait a second, right? No, sure. If it's a 45 degree, right? Yeah, then you get the same variance. Otherwise, you can play with the variance. But we're not making an assumption about the variance here. It's basically the variance of the variance, right? That is what the independence here is the assumption about, right? So effectively, Max has a question.
Yes, we're assuming a linear model.
Yeah.
Lowest noise.
Yes.
Variance.
Yes.
Is that basically what they're saying we cannot do?
Yes. Yes. So this is why it is a structure learning paper. And you can easily come up with data where no tutor is going to give you like a really completely bonkers answer, right? Really gobbledygook. Easily. Because linear and Gaussian is not identifiable. We cannot tell cause from effect. You can toss a coin, right? If you say, well, I believe lower means so the cause has lower variance and effects have higher variance, sure, then in that world you can do this. What you can in that world also do is effectively look at all your variables, sort them by variance, and the one with the lowest variance, well, that is the root cause, and we just have to figure out now, well, which ones now share an edge, right? That's called far sortability. It's a paper from a few years ago where some people, well, basically slapped around and bashed a long string of causal discovery methods. Basically, okay, well, this is fantastic what you come up with, all this pseudocode and theory, but effectively what your method does, you sort by variance and you draw these and these edges, done. So, and if you generate now data with constant variance, over all these methods fail miserably. That's the opposite, right? The other side of the medal. So, yeah. Linear and Gaussian, no go, right? Good. I'm going to walk through this slide and then we're going to wrap up. Linear and non-Gaussian is identifiable with very high probability. Effectively, just imagine a, let's say, a Poisson-like distribution, right, or an exponential, something that is not symmetric. Well, then in the one direction I can fit it, and I always need to get my brain around, okay, that if it's not symmetric, it's still independent. We're still sampling over that particular distribution, right? Fitting like a regressor with a strange distribution, okay, I would have to see which options to type in or how to implement it, but in theory it's possible, right? We can think about it. But that means that we can't just flip it arbitrarily around, like you can with a Gaussian. And even if you have another symmetric distribution, let's say a T distribution, right, heavy-tailed Gaussian, you can't arbitrarily flip it around because the tails start to, well, in this way I have sort of the nice smooth tails, right? Whereas in this, I basically get like a weird, contraption of tails, all dependent on the shape of the function. So it's not so much the symmetry, it is really the, well, the tailness in a way. Linear and non-Gaussian is identifiable. The abbreviation of this is lingam. Linear non-Gaussian, right? I mean, that's, I'm going to say thousands, but I mean, obviously it's not thousands, but I mean, thousands of papers have been published about causal discovery and all sorts of other related topics under lingam. I am personally not a big fan of this line of research. I mean, I'm not, well, bashing it, okay, people shouldn't do it, but I don't really believe that we live in a linear world with non-Gaussian noise. Linear and Gaussian is a simplification that I'm kind of willing to accept-ish, right? But linear and non-Gaussian, I mean, you know, if that would be the case, why on earth would all our regression methods with Gaussian noise, right, I mean, minimizing variance, why would they work? However, lingam has some very nice mathematical properties. You can prove all sorts of things super easily. And if you have a nice theorem, then you can put it into paper, you submit it, and there we are. So, for most cases of nonlinear functions, and egal which noise, any noise, it's actually identifiable. We already saw one example. We saw a nonlinear squiggly, over which I just drew some Gaussian noise, and you saw that, well, the Gaussian noise was not a problem. And, well, unless I choose some very pathological case of noise, then for a very specific type of shape, it will remain identifiable. That is pretty neat, right? Because the nonlinear Gaussian case, that's the one I care about most. And of course, the more linear this nonlinear function becomes, yeah, okay, the less identifiable. Identifiable is of course a binary concept, but you know what I mean with less identifiable it becomes from actual data. Good. Yeah, okay. This one slide perhaps makes sense, or this one animation. So how can we now fit an A&M? We already considered it for the continuous case, right? Effectively, what you can do is you just fit a, well, either a linear function with non-Gaussian noise, right? And then in the one direction, the other direction, you check for the dependence, done. Or you fit a nonlinear function with whatever noise, Gaussian is fine, and so on and so forth. Now, one thing to keep in mind is that what we would like to do, what we actually want to check is, are the input and noise independent? If you regress, is that strictly the goal that your regressor is aiming for? Not really. It wants to minimize error. And there can be the happy coincidence that these two coincide, but not necessarily. So you can adapt your regressor such that you, rather than minimizing error, you maximize independence between input and residuals, right? I'm not going to walk you through those details for continuous valued case, but you hopefully believe me that this is possible, right? You just have a slightly different objective. And there we are. Then this is called RESIT, for residuals independence test. If we have discrete data, this is slightly more involved, but still quite doable. Suppose that we now have an A&M, just like we had it, right? We have a function f of x. X is, these are discrete values, could be ordinal, doesn't have to be. And we have then some noise that basically shifts. Then, if we now optimize a function f, which a function in discrete land is just a mapping, right? It maps one value to another, right? And there may be some noise, things may be shifted, right? But that is done. But effectively, what we want to do is we want to minimize the entropy of x, which is just fixed, and the entropy of the noise under this mapping, right? And the mapping is what we want to then optimize over, such that we effectively what we can do, we can start with a random assignation of x values to y values. Here I randomly chose x1 to y1 and so on and so forth. And what we can then do is one of the regression algorithms called discrete regression, for each of the values of x in turn, this could again be randomized, we consider which value of y, if we change the mapping from where it's currently to which other value of y, would lead to, well, minimizing this. Because this part, of course, fixed, right? We're not doing anything there. So it might be that we swap this to y2, and in the next stage we swap x2 to y1, and maybe then we're done, right? This way we can minimize this entropy term over there. Now, the nice thing about entropy, and why do we optimize this essentially has, and we maximize the entropy, oh, no, wait, we minimize this sum. So, because entropy is maximal when things are uniform. So the moment that we can minimize entropy, we can squeeze out information, there is a dependence, right? This is basically what we're doing. We're trying to squeeze out as much dependence as we can, and well, if there's no dependence to be squeezed out, then these values will be maximal. That will be the most independent direction. I say most independent because right now we can actually reason about an amount of dependence, how many bits, right? How many bits do we need to express y given x? That's what we have here. And we can also reason the other way around. That gives a strength of dependence, which is different than in the previous setup. Whereas in the previous setup, we were looking strictly at an independence test. Thank you, Michael. Although I think it's going to be silent now again. Because a strict statistical independence test gives you yes or no, right? You get a p-value. If the p-value is below a certain threshold, okay, yes. If it's above a certain threshold, no. A p-value does not have an interpretation of being more or less independent. It is a yes-no by definition. A very low p-value doesn't make the hypothesis more true than a p-value right below your threshold. That's just not how p-values work. It's how we like them to work, how we interpret them, but this is wrong. With entropy, we do get this interpretation, allowing us to define things like this. We can minimize the quantity like this, like we just saw. And now we can compare the entropy from x to y to the entropy from y to x, right? We compute this the same way, but then we just flop the things around. And if this entropy from x to y is really much lower than in the other direction, we can infer x causes y. X has information about y, right? We can really make these things independent, and physically encoding the noise separately from x, well, it doesn't harm us because they are independent. The noise doesn't need to know the value of x. Whereas in the anti-causal direction, there is this dependence. So if we force y to be encoded separately from the noise, well, in a way, this means if we go back to the previous example, we have the value of y, but the fact that, well, that there are bands, like a longer bands, where, well, let's say the variance of the noise shifts here versus there, well, if you don't know the value of y, then you somehow need more bits, you need lower entropy than strictly to encode, or higher entropy, sorry. So in the opposite direction, if this one is smaller, then we infer that. And if they are the same, or approximately the same, right, because we only have a limited sample, we may not be able to estimate this perfectly, then we say, okay, I don't know. It's an H. I can't orient it. So now we already have two methods that we've seen, one for continuous value data, that we just hacked it, we cobbled it together, and we have one here for discrete data. But if you are now given a PDAG from PC, from guess or whatnot, for each of the individual edges, you can just do this. And well, as long as you maintain DAGness, right, because this only looks at individual edges, of course, we can actually orient things under the additional assumption of an A&M, right? So you're making stronger assumptions, but I would say these are still, well, possible, warrantable. Does this work? This plot is pretty much straight from Kailash's PhD thesis. He did his PhD 2 years ago with me. ACID is the name of the final method, called accurate causal inference for discrete data. And yeah, so I show this plot both to show that the method works, but also to give you, well, one example. If you're doing the assignments or reading any other paper, plots like these should make you very suspicious. This method is almost too good. 100% accuracy everywhere. What could possibly have gone wrong, respectively right? Here for this, it's really about the amounts of noise and whatnot, and we can, for higher dimensionality, we can break it, but the main point of this plot really is to show that, so cisc is a predecessor of acid, slightly differently defined, and as you can see, cisc works well, slightly well, completely crashes below random coin flip. Negative binomial, well, so we were talking earlier about variance, right? All the other distributions, they increase variances. So cisc, in a way, likes to say high variance is effect, low variance is cause. Negative binomial maps exactly the other way around. So acid picks up exactly this type of dependence, independence, so it's not put off track, right, off scent by, well, this different type of funnel. So acid is in a way superior. This is what this plot really wants to show. And what you can see is that discrete regression, DR, that's the method that we just saw, but then it actually really wants to do regression and not so much entropy, that actually performs quite well across the board. So if anything, this plot tells you, okay, the authors did not really try to tackle their own method, which is all true here. We really just wanted to show that for those cases where other methods start to trip, and they don't really trip for quite a large group of distributions, right? They're quite good, but there are cases where they're really completely full. And you see that DR is actually pretty good. So the real question, if you see a plot like this, what is the true contribution of orange over, in this case, dark gray? Are these few additional percentage points, are they really something worth? Or are these just bold numbers in the table? This is what a plot like this should make you think. Good. Okay, now it's still 12:02, so I'm still over time, but we had a break, so okay, I feel a little bit absolved. Thank you very much for your attention. We continue on Monday. Bit offbeat, but because next week, Friday or Thursday is a public holiday, and well, yeah, so rather than canceling a lecture, I moved it to Monday. So I hope to see everybody again there. Otherwise, see you online, or I will just wave at you like this. And yeah, and I think also next week, Thursday is the deadline for the assignment, right, at the top of my head. Monday. Okay, good. Could be. I tried to plan it, I mean, as evenly across, so it's, yeah. Yes, Monday, makes sense. Magnus?
I just wanted to ask about the exam again.
Yes.
When?
I will send an email later today. Good. Okay, then thank you very much. See you on Monday. Have a nice weekend. Bye-bye.